Well, good evening, AP Physics students. Mr. Kirsten here, continuing our discussion today about rotational physics. So on the agenda for today, we're going to be talking about kinetic energy, work, and power. So the energy systems that come about in rotational motion. So, kinetic energy, again, I think the best way to think about these things is kind of with looking at the linear and the rotational together. They're kind of analogous, and looking at them both kind of makes sense. So by now, you're more than familiar with the formula for kinetic energy in the linear sense, 1/2 mv squared. And kinetic energy, wouldn't you know it, in the rotational sense, 1/2 I omega squared, where omega is your angular velocity. One important note here, whenever you're talking about work or energy or power here, be sure that your omega, or any of your variables really, we want them to be in radians. Radians is a dimensionless unit, so it always comes out to be joules. The number 360 degrees is actually somewhat arbitrary, so if you put degrees in here for your omega, you'll come out with the wrong answer. So make sure you use radians for your omega there. Again, 1/2 mv squared, 1/2 I omega squared, just kind of seems to make sense. Again, work in the linear sense, force times distance, right? Same idea in the rotational sense, except the analogous of force is torque, and the analogous of distance is delta theta. So when you exert a torque through an angle, you get work done. And that work is measured in joules. Again, make sure you have that angle measure in radians. All right, got to have that in radians if you want the work to come out to be in joules. So I think those two kind of make sense. We're going to jump down to power. We'll talk about angular momentum in another video here. But the same idea is always true for power. Power is the rate at which you do work, so work divided by time. So there's a couple different ways you can do that. You can calculate the work using this equation and then divide it by time. Or you can think of it as, instead of force times velocity, think of it as torque times omega. And remember, your SI unit of power is the watt, all right? So yes, power is always work over time. You just have to calculate work in the rotational sense instead of in the linear sense. One more set of equations I want to kind of go through with you today are the equations that relate angular variables with linear variables, okay? And just as a quick example here, let's say I have a silver dollar and I roll it along the ground, all right? Well, if I roll it along the ground, one complete revolution, how far has it gone? Well, the only way we can answer that question is if we assume that when we roll it across the ground, that it doesn't slip, okay? So many problems you'll say, assume that, it's not slipping, all right? And if that is the case, all three of these equations work. And let's just kind of look at one of them here. The distance something goes in the linear sense is equal to the angle it goes through times the radius. Now, if you think about this, if I bring this guy through one complete revolution, like 1 2 pi radian revolution, how far did it go? Well, it went the circumference of the object linearly. Okay, so you unwrap this circumference and lay it out on the ground, and that's how far it went linearly. So the distance it went linearly is equal to the angle it rotated through in radians times the radius. All right. Likewise, linear velocity is equal to angular velocity times the radius, and linear acceleration is angular acceleration times radius. Now, notice, in order for these equations to be true, two things must be true. One, your angles all must be measured in radians, And number two, there can't be any slipping of your tire or your coin or your whatever. So, a couple good sets of equations to keep in mind. And with that, we are going to do a problem here. We're going to do Chapter 8, number 44, as an example problem of calculating energies and power and work. So, question 44 says, an automobile with engine develops a torque of 280 Newton meters at 3,800 RPMs. What is the power output of the engine in watts and horsepower? So let's dive in here. So we know the torque that the engine is exerting. We know the angular speed of the engine there. What is the power? All right. Or maybe I should say, what is the power? All right. So number one, when I'm dealing with power, I want everything to be in radians. So boom, revolutions per minute, RPM. Let's convert that right away into radians per second. So my new omega there, I'm not going to use RPMs. I'm going to use radians per second. So what is power in the rotational sense? Well, I kind of forgot, but I know it's work divided by time, right? What is work? Well, that's force times distance in the linear sense, but I can't use that. So what's force in the linear sense? Well, that's torque. What's distance? That's angle. And divided by time, but I don't have angle. I only have omega, which is angular speed per second, right? So this is kind of like omega here. So that is equal to torque times omega. So there you go. I didn't even remember the formula, but if you kind of remember your linear formulas and remember which variables are analogous to which, you can kind of figure it out. So the power of this engine should be the torque it exerts times the angular speed, which should be 280 times 398, and therefore the power turns out to be 11,142 watts. But we only have two significant figures here, so that would be 11,000 watts would be the power of the engine in watts. But when you're dealing with automobiles, we here in the United States prefer to talk about horsepower instead of talking about watts. All right. So the conversion factor, you will not have to memorize this, but it's kind of fun just to know. 1 watt is, 1 horsepower is 746 watts. So if you divide that out and round to the correct number of significant figures, you get that the power output of this engine is about 150 horsepower, right? Which is plenty of horsepower for a car. So there we go. The only thing we have left here is our joke of the day. So I'm going to try not to screw this up. This is a good one. All right, here we go. What's the difference between a cat and a sentence? All right. What's the difference between a cat and a sentence? Well, a cat has claws at the end of its paws, and a sentence has a pause at the end of its claws. Whew. All right, I thought I was going to screw that joke up. I honestly did. That was kind of a lot of words to say. So, nice job, physics students. We will see you tomorrow. Keep up the good work.